Hello guys, so I will explain about how to make the inverter using STM32. So I make this for controlling my turntable motor, but you can apply it for making another type of inverter using STM32 Bluepill. Because from my experience, I cannot find video on YouTube that explain the process to make the inverter using this uh, microcontroller. So first I will explain a little bit the step by step the process. So in here I will using unipolar sine PWM, and then to apply the theory to the microcontroller, I will using the STM32 Cube IDE, and then generate the pins, timer, and the interrupt using the IOC. And then after that, we make the interrupt for the pulse width modulation, and then make the lookup table for the output. First, what is unipolar sine PWM? So you can read on the references in here to explain more detail, but actually in short, that we need to generate pulse width modulation to make the output like this using H bridge. So in example, from 0 until 180 degrees, so S1 and S2 will be turned on, but S1 will be pulse width modulation. So the S1 will be more higher frequency than S2. S2 will be turned on the fundamental frequency. But if just follow this theory, when the switch is turned on and then the load is lower, so the current on inductor, in this case in my load is motor, so it will be the current on the inductor motor will be uh, what will be reverse, not reverse, but it will be like freewheeling. Actually, it's okay to freewheeling through the diode of the MOSFET, but if the load is have a high current, it will be make more losses on the diode and then make the MOSFET more hotter. So I will turn on the S4 in here, complementary with the S1. So the current of the freewheeling will be through the S4 diode, S4 MOSFET, I mean. So S1 and S4 will be complementary pulse width modulation with high frequency, and then S3 and S2 will be modulate in fundamental frequency, maybe around 50 or 60 hertz. So this will be slow switching, and then this will be high switching, fast switching. Okay. So yeah. So this is the calculation how to generate the pulse width modulations frequency on the STM32. And then in this case, I will use center aligned pulse width modulation. So the counter period will be counting twice from 0 until the maximum of counter period, and then from the maximum until 0. So the period will be twice. That's why in here the calculation to get a 25 kilohertz, we need 2 times 2. So it will be 25 kilohertz. So let's go to the IDE. So you open the STM32 Cube IDE. So I already have the program before, but I will make it from scratch to show the process. So you click File, New, and go to STM32 project like this, and then you type it the Bluepill IC number, so it should be this one. There will be two, you can choose one of them and then click and then go next, and then you type your name of the project. It's up to you, and after that just next and then finish. After you open that, you will found this page. If you didn't found this page, you can just double click on the IOC. It will be open this, and then first you need to configure your clock speed. So go to System Core, go to RCC. In here we will use high speed clock from the external crystal. Choose this one, and then after you choose that, go to clock configuration and click here. We will use the maximum clock speed 72 and just press enter and then OK. It will be automatically calculate all of the configuration, and go back to pin out and configuration, and then we go to the timer. In here we will use timer 1 to make the PWM pin. So the clock source setting to internal clock, and then we will use channel 1 to generate the PWM. So PWM generation, channel 1 and channel 1N. So this will be complementary switching. So channel 1 we will using pin number PA8 and pin number PA7, and then we will use prescaler 0, so it will be divided by 1, and then the counter we will type it 1439. So the counter will be count from 0 until 1439 and go back to 0, so it will be counting twice. That's why in the equation I put times 2. And then we setting the auto reload preload to be enabled, and then in here in my configuration I need around 10 ticks of that time. So for a detailed explanation of this, you can find it on STM32 YouTube for the calculation, because there is some configuration if more than, I forgot, 64 or 128, I forgot about it, but it will be different. There is some detailed explanation about this. And then the mode, using PWM mode 1, and then we don't need to change anything in here, just like this. And then I forgot something, we need to change the counter mode. The counter mode we will use center align mode 1, like this. Okay, and then we go to the NVIC setting, and we choose this one, timer 1 update interrupt, like this. And then the last thing, we need to go to the GPIO. So we haven't choose any GPIO. We can choose directly from this side. We will use PA9 and PA7. PA9 and PA10 for the other 2 pins. So setting to GPIO output. This one too. So the PWM will be use PA8 and PA7, and then the PA9 and PA10 will be switching with fundamental frequency around 50 or 60 Hertz, or anything depends on your setting later. So, and then don't forget, go to the project manager and then go to code generator and choose this one. So this option will be separating the file of the setting. So if you uncheck this one, all of the setting will be put in the main code. I use this one so it will be more easier to find the problem if you have some problem later, because it will be separating between the timer, the pin, and then the interrupt, like that. And then just that, and then we click save in here, save, and then you will meet this one, yes, and yes again. So this will be generate the base code from our configuration. So this is the main code, will be like this. So in here, if you open the core and the source, so you will have gpi.c, main.c, and all of the things like this. From here, I will just copy it from my program that I already make. So I will just copy the main, just copy to this one, yeah, like this. So close again, so close. So this is the main code. I already make some little explanation about the code, and then the library, and then the variable of that. So in here, why I have two fundamental frequency, because in my next project I will use it for driving synchronous AC motor for turntable. So I need two options for two different speed, but in here I will use just the first one, so it will be calculated in here. So this one will be making the lookup table of the sine wave. So if we go back to the PowerPoint, the presentation, yeah. So basically, to modulate the pulse width modulation to generate the sine wave, in here, in example in here, so from this side until this side, it will be 1 Hertz, and we will divide it into 2. So if we change, if we translate to radian, so 0 degree until 360 degree, but if we change to radian, this will be 0 in here, and then this will be 1 in the middle point, and then will be 0 again, and then will be -1, and then go back to 0 again. So the half of cycle, the maximum point will be 1, and then for the other half cycle, the maximum point, the most minimum point will be -1. So from 1 Hertz, by using 25 kilohertz PWM, we will it's like dividing 1 Hertz by 25 kilohertz to generate each time the pulse width modulation with different duty cycle. So the effective output duty cycle of the pulse width modulation will be the timer period, so is from 0 until 1440, and go back in again to 0 times the radian of that time. So like this. So this will calculate the lookup table of the radian. And then this the interrupt that we will be used to generate to control the pin. So this one is when the t equal of 0. So I make all of the pin will be 0% duty cycle. And then this one when the time is the half of cycle, so on 180 degree. And then this for when time from 0 until half of the cycle. So this is for the positive cycle, and then this is for the negative cycle. And then this one is for my next project, so you don't need to care about this. And then why it need to count twice and then updating? Because in the center align pulse width modulation, the interrupt will be running twice in one cycle. So I need to make sure this interrupt only call once in one cycle. So yeah, that's why I need to make this thing in here. And then after that, don't forget to include the interrupt into the interrupt main code. So you just copy the name of the interrupt and go to team.c in here, and then not team.c but interrupt it.c. So scroll down, then you will find the timer 1 up interrupt handler. So you just put this function of the name of the function, I mean, like this. And then don't forget to put it on the header of the main code. So just put anywhere like this. So it should be like this. Don't forget this one. And then the last thing that you need to do, so just save and try to build. Okay, that's all. So you will have the program inside the debug. Depends on using debug or release. So you will have the .elf, or you will have the hex of the file. It depends on your configuration, and you just need to upload it using ST-Link or serial by using STM32F103C8 programmer, or you can just using the IDE to debug. But usually I just using this program to upload it because for me it's more easier. And we will see the result.
So right now I already uploaded the program to the Bluepill, and then I make this inverter board for driving the AC synchronous motor. So this is low voltage inverter, but actually the working principle is same like the high voltage inverter. So I feed the board with 12 volt and then low current because just for testing, and then I utilize the boost converter in here to boost the 12 volt from the power supply to increase to around 31 volt, and then make around maybe 20 something volt AC. So in here I just want to test the program. So I already connected to the oscilloscope, and this is the waveform result from the inverter board. So in here the frequency should be around 50 hertz, and then this is the output voltage RMS, and then this is the peak to peak. So yeah, I think the program is work. So right now you can use it and modify it based on your need. And then don't forget, actually because this is sinusoidal PWM, so you need to put some output filter to filtering the PWM to make the output pure sinusoidal AC. Okay, thank you.